Hello and welcome back to Calculus2. We are starting chapter 10, preparation for Calc 3. We're talking about parametric equations first. So by now you probably figured out that I like to first give the definition of in terms of what something is. I said that limits are just computing the y value. It's a fancy way to compute the y value, more advanced way to compute the y value than just plug the number in the function and get it. I also talked about the derivatives and said stuff like the rate of change, and the derivative is the function which generates all slopes of the tangent line. It measures the change, calculates the change. And then the integrals are computing area under the curve, but the actual idea of the integral, because it calculates net area, is it calculates accumulation. So now, what are parametric equations? Parametric equations utilize a parameter to break dimensions of the problem into sets of equations. So when I write equation, let's say y equals x plus 3. This is a 2D equation because it can be graphed on the 2D space, which is so it looks like this. This is what it is, right? Now you see two dimensions here. There is a dimension x and dimension y. And what parametric equations do is they separate these two dimensions, and each dimension will have its own equation. So I can define parametric equations as a set of 2 for 2 dimension, 3 for 3 dimension, 7 for 7 dimensional space. It's okay, linear algebra is coming, all right? So the parametric equations will have the number of equations equals to the number of dimensions. So one equation per dimension. If I want to break this particular equation in parametric equations, I have to have equation for x and equation for y dimension. If I choose to operate with, let's say, parameter t for time, I can say let x be t, in which case y would be t plus 3. This is a set. You can use this brace to kind of group them together. And in Calc 3, you are going to put these in a vector, and you will use them as a vector. It will call vector value function and so on. We're going to have a little different name for it, but it's going to be that, and it's going to be used a lot. So you observe here that you have dimension for x and dimension for y, and they are connected through t. If you want to put these equations back together, you will solve in one of them for t, and you will plug into the other, and that would eliminate t's, and x and y will reconvene. Why are we doing this? Calculus is mainly applied to functions, but we know that not every expression we write is a function. You take circle, for instance, whose equation is
x squared plus y squared equals r squared.
Very good. Let's use 9, right? Circle with radius 3. Is that a function? The answer is hell no, right? Can we differentiate? Sure. Can we integrate? No. So what are these parametric functions good for? Well, it turns out that if I am to transform this into parametric set, we are going to get set of functions. So x is going to be 3 cosine theta, and y is 3 sine theta. So right now I am telling you that these are equivalent. So you have the form x squared plus y squared equals 9. It's not a function where the parametric set underneath each individual one is a function. Now, you look at this and you want to know how to convert back. Well, I told you, solve for theta in one of these and plug the expression into the other. So let's convert back to xy. I will take the first equation, or you can do second, it doesn't matter, and you solve it for theta. Theta is definitely inverse cosine of x over 3, right? You move the 3 first over, and then you take inverse cosine of both sides. Then you plug in. You will get that y is equal to 3 sine of inverse cosine of x over 3. Now, some of you will recognize this construct here from your pre-calculus 2 when you were asked to simplify these problems, but you didn't know why. Welcome to the part where you need it. The way to transform this is to draw the triangle on the side, and assigned, you know that the cosine is adjacent, right? If that's theta, it's adjacent over hypotenuse. And if you use Pythagorean theorem, the third side will be 9 minus x squared by simple Pythagorean theorem. Now, you will write inverse sine looking at the triangle, because sine and inverse sine cancel each other. So when you write the inverse sine, it is going to be the square root of 9 minus x squared over 3. This is where inverse sine and sine kill each other, and then 3 and 3 also, and you get y is equal to square root of 9 minus x squared. You will square both sides. Y squared equals 9 minus x squared, from where there's your x squared plus y squared equals 9. So this was a transformation which took you from the parametric set into the xy, and I would argue that this is one of the harder ones out there, because you had to do all of these extra steps. Now, in most cases, this calculation is far easier, because you are mainly dealing with some types of polynomials and so on for practice, and then you get to see crazier stuff later on.
I got a quick question.
Yes?
So how did you replace cosine inverse with sine inverse?
I created the triangle using the cosine, and then I read the triangle and used the sine.
Okay.
That's how. So now I want to make the air quotes definition over here about circle. Parametrization for the circle is r cosine theta y equals r sine theta as the set. More general, which is ellipse, is going to be x equals a cosine theta, y equal r sine theta. Not r, sorry, b. I hope that you know that circle is the special case of the ellipse, because ellipse has the major radius as and the minor radius, so two different ones, and if they are the same, the equation collapses onto a circle. The equation for the ellipse, I'm going to erase this. The equation of the ellipse is x squared plus a over a squared plus y squared over b squared is equal to 1. When a is equal to b, you call it r, right? Then that r is a common denominator which goes and multiplies 1, right? So circle is just a special case of the ellipse, and their parametric equations must be the same, except the circle is going to use the same numbers r, and ellipse is going to use a and b. Now clearly a is going to be the radius in x direction, so that will be horizontal count to the left and right from the center, and b count up and down from the center. So in some sense, parametric equations are much easier to graph also than, right? So if you recognize the ellipse from parametric equations, let's say you have x equals 2 cosine theta, y equals 5 sine theta. 5 is too much. Let's go with 4. 4 is too much still, but anyway. You are going to put the center wherever the center is, and then you are going to say x cosine 2 units left and right, 4 units up and down, and there's your ellipse. It goes very, very quickly. So this is 2, this is 2, this is 4, this is 4. So it's a very quick way of, right, following this. The theta or the t or whatever you choose to be, it's called the parameter. And these equations are using that parameter as the independent variable, and each of the dimensions of the original problem treats that as a dependent variable upon that parameter. So let's say that you have x equals 3t and y equals t minus 1 squared plus square root of t. What is the equation that we have? What is the, so this is a parametric set. What is the xy equation when you combine them? So where would you start?
I would start with dividing the 3, x divided by 3 equals t, and replace all the t's with x over 3.
Good. So we are first going to solve for the parameter in one of the two equations. Common sense would say, do it in the first one, right? And then we are going to replace that in the second equation, so x minus 3 is 1 plus square root of x over 3. Now you might want to, you know, simplify this or so on, but this equation over here is already your answer. I forgot to square. So you can square everything out and, you know, do these things. But we are technically done right there. The harder thing to do is to parametricize. When I give you the equation, you are supposed to come up with parametric set. So let's say that you are supposed to parametricize line segment from, let's say, 1, 1 to 5, 5. This is one of the simpler problems. Now, if you want to visualize this, you will clearly visualize 1, 1 and 5, 5 and just a straight line that connects those 2 points. So now the question is, how would we write parametric set for this? And then also, what is the domain for that parameter? Is it from negative infinity to infinity? Is it from 1 to 0? Is it, you know, or 0 to 1, or what is it? So the clear course of action over here is to first create the y equal mx plus b for the line, right? We see that the slope is 1. and it's going to go through 0, right? So it's just y equals x. So this is an extremely easy thing. If you say x equals t, then y is equal to t as well. And t needs to be between what values?
Between 1 and 5.
1 and 5, very good. So here is your parametrization for this line, right? Your t needs to be between 1 and 5, and you see that you're getting x equals 1 and y equals 1, and then eventually x equals 5 and y equals 5, right? To satisfy both points. But you actually have everything else in between, and x is always equal to y, right, on this straight line. Spicier example would be when you don't have the line to be this nice, right? So let's say, so this is example 1. Example 2, let's say you have 3, -2 to 7, 11. I just had to do it. So you are going to do algebra first to find the equation of the line x, y equal mx plus b, and then you are going to parametricize that. So let's do it. We first find the slope, which is 13 over 4, right? It's 11 minus -2, that's 13, and then 7 minus 3 is 4. So slope is 13 over 4. Then we use one of the points to find b. So if y is 11, no, I'm going to use the other point. If y is -2, and then I have 13 over 4 times 3 plus b, we have that the b is equal to -2 minus 39 over 4, which is 8, and 39 is 47, so -47 over 4. So y equals to 13 over 4x minus 47 over 4. That's my equation. So we can multiply through by 4 and have 4y equals to 13x minus 47. And then from here, say that 13x, let's say, is equal to t. If 13x is equal to t, then x is equal to t over 13. That's already one of your equations, right? The second equation, you remember that you replace 13x by t. The second equation is 4y. Let me put it here. 4y is equal to t minus 47. Solve this for y. Y equals t minus 47 over 4. Now this is annoying problem, right? So here's your parametric set. X equals t over 13, and y equals t minus 47 over 4. All we need to do is to figure out what are the two values in between, right, what drive the parameter t. And all you need to do is to fit the first point, which was 3, -2. So what value do I need here to plug here to get 3 over here? We need 39, right? Because 39 divided by 13 is 3. Now if you use 39 down there, 39 minus 47 is -8, divided by 4 is -2. That one falls in immediately, if you did algebra correctly. And the second point was 7, 11. So now to make 7, that's 7 times 13 is 91, right? So parametric set for this one looks terrible, but as you can see, it's possible. This is kind of stuff that you will be doing, plus circles, plus ellipses, and stuff. Now, also quadratics, and so on. The next example would be quadratic, on how to transform the system. So let's say you have y equals x squared plus 4x minus 3. There is always a cheap way out to create parametric equation set, and that is you simply define x to be t, and then you just replace all of the x's with t's for the y. We call that dummy substitution, all right? No, because in some cases it works, right? But sometimes there are better options if you, let's say, perform completing the square. It will give you a more simplified version in one of the equations, right? So let's say you do the dummy parametrization. You would have x equals t, y equals t squared plus 4x minus 3. So you technically didn't gain anything from here. You're still dealing with the same polynomial, right? That's what I said. Please pay attention. It's clearly 4t. Look. 4t. Right? Great. Now, what I can do is I can do completing the square. So I can say x squared plus 4x plus 4 minus 3, right? This is the completing the square part. Half of b squared. So half of 4 is 2, squared is 4, so add and subtract. And now the first part over here is going to be the parenthesis of x plus 2 squared minus 7. If I make this to be t, right? If I make this to be t, I'm getting x equals t minus 2 and y equals t squared minus 7. Would you agree that this is easier to work with than the other one? There is no reason for us to use this dummy parametrization because we are working with the exactly same expression, which we for some reason didn't like and needed parametrization, right? So we tried to find the other way. We tried to find different equations that might suit our calculations better. So this is one of those parts where you're learning something that you don't see how to use until it hits you in Calc 3. I mentioned that situation prior with the sine and cosine calculation, right? Those were the problems that were shoved down your throat. Do this, right? And then you had to wait 2 classes for it to be used. It will be used again in differential equations. The same triangle thing with the cosine and inverse sine and so on. So the whole thing here now is you're learning it for later, and it will eventually be used. So dummy parametrization is always possible, but it doesn't provide you, wanted results. Where parametrization done properly will change equations in your favor. So that's one thing that we need to know. Now, these parametric equations introduce, on top of your original 2 dimensions, x and y, they're introducing another variable called a parameter, t for time or theta for angle or whatever else. Since you are introducing another variable to the problem, that means that you have another degree of freedom that you can exploit for some kind of application. And what you gain with the parameter is another property for your functions now for your graphs, and that is orientation of the graph, motion along the graph. If I write y equals x squared plus 4x minus 3, all I can do is draw a graph. But if I write x equals t minus 2 and y equals t squared minus 7, which is the same graph, I will also have orientation of motion along that one. Now, that might not make sense now because we just started talking about it, but I want to show that using circle. So if I have x squared plus y squared equals to 9, by the way, I practiced drawing circle a lot, so that's not how you draw a circle. What happened? Out. So this is the circle with radius 3. Parametric set for this is x equals 3 cosine theta, y equals 3 sine theta. I told you that, and then we converted it back to verify, right? Now observe what you have. Theta is going to be between 0 and 2 pi. So theta starts with 0. Observe that theta equals 0. Cosine of theta is, cosine of 0 is 1 times 3. So this is a position for theta equals 0. Theta can be pi over 2, right? When theta is pi over 2, how much is cosine of pi over 2? 0. And how much is sine of pi over 2? 1. You are getting this point here for pi over 2. And then this point here for theta equals pi. Do you see that there is a motion counterclockwise? All right? Counterclockwise motion, right? So, with parameter, we have an extra degree of freedom which manifests itself as orientation of the graph. So, orientation of the graph is the direction in which the graph is constructed. Which gets us to graphing parametric equations. We employ the middle school method. When you are graphing parametric equations, you are going to compute points, just like in middle school, okay? Except this chart is going to have 3 columns. One column is the input parameter t, second column is x, and the third column is y, and you will be just plotting xy, obviously. So if I give you a parametric set, x equals t minus 2, and y equals t squared plus 1, actually t squared minus 2, and let's go with t plus 1. How about that? So let's use this as a parametric set. You could convert this into a parabola and then go, good luck graphing it, right? You have to find the vertex and you have to spend those days figuring it out. But look at this. You pick values for t. You say that your domain, let's say, start at -2, -1, 0, 1, 2, 3, whatever. And you compute your x and your y values by plugging t in equations. So when t is -1, you get -1, 0, 1, 2, 3, 4. Then you compute y values. T squared, that's 4 minus 2 is 2. 1 squared, -1 squared is 1, minus 2 is -1. 0 squared, so that's -2. 1 squared is 1 minus 1 is -1. 2 squared is 4 minus 2 is 2. And 3 squared is 9 minus 2 is 7. I hope you see that you have x, a point xy, another point xy. You can plot that on a graph. So this is literally the middle school method on how to graph these things. So we have -1, 2. So where -1 is 1, 2, 3, 4. That's all we need for x. On 0 is -1. On 1 is -2. On 2 is -1. On 3 is 2. And on 4, which is the last number we have, is 7. 3, 4, 5, 6, 7. And there it is. Now observe that we started counting here. So the orientation of this graph will be this way. Now this graph will go on forever because we did not limit that in any way. I'm just going to say start.
May I ask, is it important to draw the arrows as a way to indicate which direction it goes to?
Yes, which is called the orientation. That's what the arrows are. So time flows forward from -2 to -1 to 0 to 1 to 2 to 3 to 4. So as the time progresses forward, the points evolve in certain order as you follow, right? So this is technically like connecting the dots in a coloring book, except you don't have to color, right? You follow to the points. So for graphing parametric functions, we are going to use the chart. You will pick values. Guys, if those values are given to you, you are stuck with those values. Remember, right? If the values are given, you are stuck with the values. The first value is 39, then 40, then 41, right? You can also use 39.7 if you like pain. That's okay because this is continuous, right? Has nothing to do with our sequence is a series that only have integers. So your domain could be 0 to 1, right? 0 less than t less than 1, and then you have to use all the decimals in between, like a half and a quarter and so on. Well, not in that order, by the way. So you are able to graph because you know how to compute values. As I said, middle school method of graphing. Compute points, plot points, connect points, walk away. That's it. The last part is the derivative using parametric equations. Why do we want to know dy dx derivative? Because parametric equations can really describe some really awesome graphs that are not functions. And even if you get some graphs that are not functions, they still have tangent lines, right? And a tangent line implies that there is a derivative somewhere. So now you have the choice of converting parametric equations to xy equation, which is not going to be a function, and unleash the implicit differentiation, or you can find the derivative dy dx by differentiating y in respect to parameter and divide that by differentiating x equation in respect to the parameter. Right? I hope you see that derivatives dt and dt cancel. Right? The software just crashed, which means it will be crashing from now on. Now, I think this fixes it. What happened? Yeah, for whatever reason, if I do that on the side, it doesn't crash.
We were just talking about how this doesn't crash.
What? Oh, the Apple thing? Let's go with the less insulting answer. My Surface Pro 3, which used to run Windows 8.1, didn't crash one note even once. Flawless. Surface 4 with Windows 10, constant crashes. So eventually it will be updated and patched, but I guess Windows 10 is still brand new in that respect, that, you know, usually I upgrade Windows after like a year and a half, you know, after it's pushed to the market. My main machine at home still runs Windows 7 actually. I have zero crashes, everything works flawlessly. I haven't seen a glitch 10 years now. Well, I have it on other 3 machines. I have Windows 10, but main machine 7. That's the, you know. Anyway, for whatever reason, guys, and I can't explain it, this fixes it. If I try to write the equation immediately after the crash, it keeps crashing, keeps crashing. I restart, it keeps crashing. I draw this on the side, and it just works. It's some kind of magic there. They're onto something. So, if we want to, you know, further discuss this, we will say that x is f of t and y is g of t, 2 different functions. Well, there's a crash again. What the hell? I know. Yeah, I think the issue is with the cloud. It's not syncing, which is why I disconnected the cloud last time. When I disconnected the cloud, it's just I mean, luckily we're done. We just need to do example for this.
It's doing the board.
Yeah, well, I restarted and it works, but it just kills the stream. I'll try one more time. If it crashes, then we'll kill the stream, restart, and that's it. So these are the functions, and then you have your dx dt f prime of t and dy dt g prime of t. That's what I said. And what happens here is dy dx is just g prime over f prime. Most of the mistakes that students make is because you usually work on x first and then on y, you put f over g instead of g over f. Like that's usually it's just a silly, careless mistake. So just pay attention. Try not to do that. All right. So I'm going to go into homework assignment and find one of the tangent line problems, which will end this lecture. And then we're going to dig into review. For the review, I'm only going to do the list, and then I will take your questions and stream the entire process on Monday. So example for this, hopefully technology holds. Example is going to be 68 x equals e to the t, y equals ln of t plus 1, and we want to find at t equals to 0. So dy dx is the derivative of a y function, which is 1 over t plus 1, divided by derivative of x function, which is just e to the t. The slope of the tangent line is the derivative computed at t equals to 0, which is 1 over 1 over 1, which is 1. Right? T equals 0 gives us 1. And then we have the slope. Now I have to find xy point so we can find b, right? So xy point is x computed at 0, which is 1, and y computed at 0, which is 0, right? Because t 0, 0 plus 1 is 1, ln of 1 is 0.
So what happens if you plug? I'm just wondering if you plug in x equals let's try and see how you got the 1.
Which one? This one?
The one on the x point.
This one? I plugged 0 into x to calculate e to the 0 is 1, and then I plug into y equation to find y value, right? So I found x and y coordinates of the point for the tangent line. So now I have the x and y, I have the slope, so y equal mx plus b, which is y 0 is equal to 1 times 1 plus b, b equals to negative 1, and there's the tangent line, y equals x minus 1. Okay. So that concludes the tangent line problem. You will be using parametric set to compute any relevant information, right? You need a point, you go back to parametric set, it's x equals y equals, you compute the point. You compute the derivative of each of the functions, divide them. Make sure you put the y equation on top, right? The most mistakes happen when you go e to the t divided by 1, right? Because this one was on top, you finding the derivative. Remember that the y equation goes on top. Y equation goes on top. It's dy over dx. And you compute at t equals 0. You find the slope, you find the point, and then regular algebra to find the tangent line. And that's 10.1. So parameterization, and you know, we were going to have one problem. We must have a problem on that in at the final. But you will be sick of parameterization in Calc 3 as soon as you jump in. Calc 3 is very heavy on parameterization. Trying to remember if they even show up in differential equations. I don't think so. So your Calc 3. That's it for this lecture. Let's talk about the list. By stream.